Okay, a single coil of wire, as a single coil of wire, and its plane is parallel to the uniform magnetic field of flux density B. You're supposed to assume that it's 3 dimension. This is horizontal. The coil is rotated through a horizontal axis as shown in the diagram. So the dotted line is the axis. It's turning around. Sketch a graph to show the variation of magnetic flux through the coil as the coil rotates through a complete revolution. One revolution means one round. Clearly mark the value of the angle, the plane of the coil, and the magnetic field. Okay, so you can see that it's very nicely done. You can get it from internet, this picture. Right? When it's horizontal, no area, so it's 0. If it's 90 degrees, 1/4 of a cycle is maximum. Then when it go back to another quarter of cycle, that means half a period or 180 degrees, it's flat again, no field. So you should be able to draw all this. After that, another quarter, which is 270 degrees, is a complete flux, minimum flux. After that, back to 0. Ken, what is the magnitude of the flux through the coil? Maximum. Yeah, what's the maximum flux through the coil? Yep.
Maximum.
Maximum flux through the coil.
The magnetic flux is maximum when the plane of the coil is perpendicular to B.
Value?
Theta equals to 90 degrees.
Value. What is the answer?
Value?
They give you area A, flux density B, so they want you to give an answer.
A sine 90.
Yeah, BAN, single coil, N is 1. Right? When it's 90 degrees or 180 degrees. Right? Minimum, usually you think of it 0 rather than think of it as negative. So it is 0 at 0 degrees, 180 degrees, and 360 degrees is maximum. Right? Maximum at 90 degrees, and at here, right? Here is sometimes it's not called minimum lah. Depends on how you interpret it. If you look at magnitude wise, it's a maximum lah. Okay with that? Right? We are basically solving problem, magnetic flux, Faraday's law, and Lenz law using that. Okay, let's go to the second question then. A circular coil of radius 0.1 meter with 50 turns is placed in a uniform magnetic field of flux density 0.56 Tesla. Initially, the plane of the coil is at right angle to the magnetic field. Right? If it's at right angle to the magnetic field, calculate the initial magnetic flux linked with the coil. So how to calculate? What formula do I use?
NBA.
Okay, BAN, easy to remember band rather than NAB. Up to you, it's your choice. Whichever is easier. Then B is given. A is by R square. N
Because
is
circular.
50. I should be able to get that. Give a unit Weber. The coil then turns through an angle of 30 degrees. What is the magnetic flux linkage with the coil? Okay, how to calculate?
One minute answer. NBA cos 30.
Okay, good. That's all. Simple answer. Cos.
But like, how do you know when to use cos and then sine, Acha?
If you use sine, you must remember that the coil make an angle of theta with the field. You are using cos because you are looking at basically the normal, right? Normal making an angle of 30 degrees with B. Right? Yeah, whether depend on whether you are using vector dot product or you are using the normal BAN sine theta. Okay. Right,
Okay.
refer to the note. This one is the angle, right? This one is the angle, the area made with the original direction. So it's the same as the angle that the normal made with the field. That's why you use cos. Okay, let's go to the next one. A small search coil of radius r and n turns is positioned so that the center is at a perpendicular distance x from a long straight wire carrying conductor. Right? So there's a long straight wire carrying conductor. Search coil is basically a coil, that's all. Usually you use it to measure the magnetic field. Right? It's just a coil. Draw a diagram to show how the search coil should be positioned so that the magnetic flux linkage through the coil is maximum. Clearly show the direction of the current and the direction of magnetic field. Okay. Okay, Ken? Draw a diagram to show how the search coil should be positioned so the magnetic flux linkage to the coil is maximum. How do you position the search coil with respect to the wire so that the flux linkage is maximum? Yep. How do you draw? Ken?
What is that? The current goes down.
How to draw? Remember, the field around a current carrying conductor is circular. Circular. So it means that if you look at it as 2 dimension, it's going to come out one side and then go in the other side. So how are you going to draw? Come out means perpendicular one side lah, and go in perpendicular the other side. Yep. Can or not? You want maximum, the area must be perpendicular to the field, not at an angle. Yeah, let's draw. Either up or down, doesn't matter. The current up or down.
It doesn't matter.
Doesn't matter. The search coil is just there, that's all. Right? Basically, it's the thumb represent the current, and remember it's circular. So it's, in this case, it's coming out from one side and then going at the search coil end. So it's perpendicular to the surface there. So you want it to be stronger nearer the coil. You want to be weaker, further away. Clearly, B, derive an expression for the maximum flux linkage. How to derive? What formula to use?
Magnetic flux linkage equals to NBA. BAN lah.
Okay, NBA or VAN doesn't matter then. How?
B is equals to U. I mean this nano I over 2 pi x.
Okay, you need to know the formula. Mu naught I 2 pi x. X is the distance. That is for B. And then A is just your area of the coil, pi r squared. Since they give you the radius. And N is the number of turns. Then simplify, cancel the part pi. Get the formula, the answer. Okay with that? Any comment? Anything not clear?
No, all clear, sir.
Okay, let's go to the next one then. Checkpoint 17.2. A bar magnet falls through the magnetic flux flat circular coil. So that is your flat circular coil. They're very kind to draw for you. As shown in the diagram. Determine the direction of the induced current in the coil when the north pole of the magnet is entering the coil. Right? So we are applying Lenz law. So where's the direction of induced current? Yep, they're kind to you. They'll give you the hint. They use Lenz law to explain your answer.
As the end pole of the magnet approaches the coil, the induced current must produce an end pole on the opposite to repel the magnet.
Yeah, so what direction should it be? You are supposed to draw it
anti-clockwise.
Okay, good. Why am I so fast? Okay, anti-clockwise. It's the north pole to oppose the motion. All right. Current is anti-clockwise. So when it's leaving, right? Remember, you want to oppose. That's why it is a north pole there. This part there to oppose it coming in. When it's leaving, yep. What's the answer?
As the S pole of the magnet leaves the coil, the induced current must produce the N pole on the lower side to attack the magnet. Therefore, the induced current must be clockwise.
You mean looking from where? Yeah, supposed to show on the diagram. Looking from where is clockwise? Okay, so when the coil is leaving, Lenz law tells us that the coil facing the magnet will try to pull it back. So it will be a north pole there. So the current is clockwise as seen from the top. Okay, let me just draw. It's better to draw the direction rather than describe clockwise or anti-clockwise. Because clockwise or anti-clockwise is relative. Right? Show a direction easier. So the next one is still the same. It's still the same, except it depends on where you look at it. Am I right? It's yeah, it's the other way around. Better show on the diagram, easier. Okay, that's how it should look like. Okay, let's try number 2. The two coil X and Y, right? That's your X, that's your Y, are arranged coaxially as shown in diagram. Coaxial means you draw a line at the center there, you pass through them. That's your axis. Coil X is connected in series with a battery. That's your battery, that's your switch. Mark the direction of the induced current in Y. At the instant the switch S is closed. Right? So you're supposed to, S is closed, that's positive. So the current is going to flow this way. If you look it from the right, it's going to be clockwise. So what should it be in Y? Yep.
Oh, anti-clockwise.
Anti-clockwise. You look it from the right or look from the left?
Look from the right.
Why do you say it's anti-clockwise? You are applying Lenz law, that's all. Right? Lenz law tells us that the coil facing each other must repel. Right? So that it must have the same polarity. Right? So anti-clockwise, if you look from the right, okay. Right? Both of them, the current, easier to say that they repel. Right? Repel. So repulsion, we are looking at chapter 16. The two current must be opposing each other. Okay, let's look at B. At the instant the switch is open, yep. First part, the switch is closed, the current is rising. So you want to oppose the rising of the current. That's why you have to be, if you look from the right, it's anti-clockwise.
They only say mark the direction, like sir, they never say to explain.
Best to mark direction rather than describe, because if you describe, don't describe properly, it depends on where you look at it. Clockwise or anti-clockwise is very, very blur. Depend on if you look from the right or from the left. Yep.
Yeah, that's all that, sir.
Say, you mean the same, is it?
Yes, the same.
You open the switch, the current is going to go down. So you want to help the current, keep the current going. Right? So the polarity facing the other is the same as Y. Trying to induce a current to keep the current in X going. Okay. So both of them are in the same direction. They attract each other. Okay with that? Okay. We are just using Lenz law. Applying Lenz law, that's all. Right. The next part you can either use, as I say, that formula with Fleming's right-hand rule, or you can use a vector method. Example, that one you must place your hand, your right hand, right, parallel to V, perpendicular to the diagram or to the screen or paper, and then you turn V to B, then you get your thumb as your direction. Okay, a linear conductor PQ is moved with a velocity v in a uniform field. Mark the direction of EMF induced in the conductor. Okay, for A, the conductor is moving to the right with velocity v. Where's the induced EMF? Right? The first right-hand rule, that's your right-hand rule. To remind you, thumb is the motion or force. First finger is your field. Second finger is your current. So what's the answer? The conductor is OP, blue color. Yep. In or out? Yep. In or out?
Mark the direction.
Use your Fleming's right-hand rule.
Q to P.
Q to P.
Mm.
Okay, let's see. Okay, correct. Q to P. How about B, where the conductor is moving up? The field is to the right. The direction of the current. Yep. Fleming's right-hand rule. Right, that's your field. The first finger. Your thumb is going up. Right? Thumb is going up. Your field is this one. So you just turn the finger the other way. That's all. To the right. So what is the answer? O to Q to P or P to Q?
B is Q to P.
Okay, the same direction, Q to P. Good. How about number C? C now
P
you
to
must
Q.
be able to read. It's moving to the left. Conductor is moving to the left. The field is going in. Remember that. It's going into the page or going to the screen. So your field must be, your first finger must be pointing into the screen. And then the motion must be to the left.
This is the must use the right hand, right?
Yeah,
right hand
always
rule.
right hand. Induced one is always right hand. Right hand.
Okay.
Field is going in. Your velocity is to the left. Or motion is to the left.
Oh yeah. P to Q. Mm.
Yeah.
Going down.
Going down or going up? Going down or going up? Okay, you're right. I'm just a bit naughty to make sure you are confident of what you say. Okay, good. How about this one? A rectangular coil of dimension A times B is released from rest outside a uniform magnetic field. So this one show you the magnetic field is going into B. Magnetic field strength is B at right angle to the plane of the coil. The diagram below show the coil is entering magnetic field. The coil completely in the magnetic field. The coil leaving the magnetic field. The instantaneous velocity for the coil is U. That one is U. That one is V. That one is W, as shown in the diagram. Right? Write the expression for the EMF induced in the coil, if any, in A, B, and C, and the direction of the induced current. Okay. This one require you not only to write the use Fleming's left-hand rule, required to use the equation E equals to B LV. So what is A? Where's the current? The direction of current. Remember, the field is going in. Right? Left-hand rule, field is going in. Your motion is going down. Yeah, field is going in. The thumb is going down. Our first finger is into the page. So where's the second finger that represent the current? That should be
anti-clockwise.
okay. Anti-clockwise, good. How about the value? What is the answer for E?
They didn't ask that.
They got that.
Ah,
EMF induced, right? Expression for the EMF induced in the coil. Expression means the formula.
oh, BAU.
Okay, we have to upgrade in a while. Okay. EAU good. Right? Only this side contribute to the EMF side. How about B? How about B?
No EMF because it's in the middle. I remember you saying this to me.
Yeah. You can either think of it as the flux doesn't change, nor flux
If it's
change,
in the
nor
middle means
induced
you did tell
EMF,
me automatically no EMF.
or the two current on this side, and this side are parallel to each other. So they oppose each other. So it's zero. Okay, good. Okay, how about the last part? Coming out. Yep.
Clockwise.
Okay, good. Same as this direction, except you direction goes to the top there, so
Opposite.
it's clockwise. Right? So it's BAW. Okay,
Yeah.
any comment? If not, we take 5 minutes break.
No.
Okay, we'll end here since our time is almost finished. So I'll take 5 minutes break. Then we'll
Okay.
carry on. Okay, take 5 minutes break.